Thanks for watching this clip from my new podcast, In Search of Soil. For more great clips and full episodes, check out the links in the description below.
I'm going to give you a pile of fresh hardwood wood chips. So it's a blend of leaves and branches all ground up. And you want to break them down as fast as possible. That's the goal. That's what we're trying to do. And we can't reduce the particle size by grinding them finer. It just is what it is. How would you go about doing that, or how would you think about doing that if you wanted to speed it up?
I mean, my go-to would be your ever ready, ever willing garden giant mushroom, Stropharia rugosa annulata, especially with the substrate you described. I mean, that mushroom, if any of your listeners or yourself have grown it, unless you pour poison on it, it'll rip through almost anything, especially fresh wood chips. But your turnaround there, I mean, just raw wood chips is a good example. It might still take two years, 2 seasons for it to really become essentially topsoil. So it's not depending on your standards, your meter might not be super quick relative to spreading those out in a wood lot. I mean, it's incredibly quick. It might take many years for that to really fully break down to be not as visible. So that's a good mushroom. Again, going through the systems we were just sort of discussing, perhaps we need a better system, the right targeted complex of molds and not so much molds are good for wood decay, but rather the white and brown rot wood decaying species, which are typically more mushrooms and larger, more evolved fungi. And the Stropharia is one I have a lot of experience with. It's just such a killer mushroom, just eats kind of anything so fast. But there might very well be, there's roughly 2,000 white rot species and about 200 brown rot species. And, maybe there's some that are out there that are just not commonly cultivated. They're not even edible. The fruit body, the mushrooms aren't edible. Not a lot of human history, but the mycelium would just rip through those chips like no one's business, way more than Stropharia. That'd be great to find out. Great question. Again, we don't have that great protocol, the refined protocol in that approach just yet. Makes total sense. There's a lot of species to trial there. Probably some obvious choices if I was to kind of go through the list to start with, but I haven't seen anybody do a sort of comparative study with something like that.
If you were in a lab and you could control the temperature on that pile, is there a temperature you'd push it towards to try and speed up the rate?
Well, probably for like a white rot species, I mean, they're growing on trees, and so they're not going to be like in a hot compost pile or some sort of decaying pile of organic matter in the natural setting. So it's going to be a more or less mesophilic temperature range, meaning from it's going to be within that range, which is on the low end, in the 30s up to a little over 100. Most mushrooms, where we have a lot more data, which is where all the cultivation, the lion's share of our cultivation knowledge comes from, is the gourmet species, edible species, and medicinals. The majority of them, they sort of have a sort of a growth curve or an optimal growth temperature, and they grow a lot slower at the lower temps. Maximums roughly in the 70, 75 degrees for a lot of species, and then you get diminishing returns with higher heat. So it would depend on the species that we would trial in this hypothetical experiment. But to throw its mycelium in there, keep it moist. You're just trying to get the mycelium to grow. You don't care about the fruit bodies in this example, which is great. Growing the fruit body, getting the fruit body to form is the hardest part of farming, mushroom farming. Growing mycelium is super easy, so long as you keep it from drying out and don't make things too dirty where it has to spend a lot of energy fighting off competitors. You create the right conditions where all it does is mostly just eat. And good, nice food, like you described, is a good starting place. Right amount of Goldilocks water. And, good temperature, which I would, as a starting place would be 75, but depending on the species, might be a little bit warmer or something.
In terms of moisture, that's another point that a lot of people talk about. I mean, you want it drier? Do you want it wetter? Is it that wrung sponge kind of amount of water?
Yeah, typically, I mean, again, pointing to mushroom cultivation, and this is what we find with growing the majority of molds and other microfungi on substrates, is you're going for the depending on the substrate, it doesn't always apply actually by definition, but the phrase that's thrown around is field capacity, where it's holding as much water as possible without so much filling the void spaces with large water droplets. So there's still a bit of microscopically there's airflow through the material, but it's fully saturated. So for different growing medium or substrates, the amount of water and how you sort of measure that, usually by feel on the farm, will vary a bit. Roughly, we say it's between like a 60 to 65% moisture content, meaning that if you take 100 grams of the material and you've hydrated it to the point you think it's done, and then you dehydrate it in the oven, it would come out at, say, 35 grams. So you've lost 65 grams of water, meaning that it was at 65% moisture content. So those are, again, sort of starting places, pretty good rules of thumb, but a lot of fungal cultivation, molds or mushrooms usually stick around that range when they're describing the preparation of the media.
From emailing back and forth, one thing you weren't totally sure of was oxygen rate relative to the decomposition rate. But in thinking about, an anaerobic pile, in the center of that pile, there's either low oxygen or there's no oxygen because it just can't get there. Are there fungi that can operate in ultra low oxygen environments? So if you did have that pile go anaerobic, could there be some fungi that could operate in there, or do they have to wait for the anaerobic bacteria and other organisms to kind of run their course, and then soil organisms come in, aerate that, and then the fungi go in?
Well, I mean, yeah, there's a great example is the yeast that makes our beers and breads. It's an anaerobic species. Yeast are fungi. They're single-celled. The 99.8% of fungi probably are filamentous, having a network of mycelial tissue, and a tiny amount are single-celled yeasts. But the yeast that makes our beer and bread is an anaerobic species. There's yeast all over wild plants, wild fruits. There's yeast everywhere. We know very little about the role of soil yeast, which is a category of soil fungi, very poorly studied. There's yeast throughout the oceans, there's dissolved oxygen in oceans, obviously, so the fish can breathe, but it's very low oxygen levels, in lower depths and things. So there's anaerobic, there's fungi that can also survive, filamentous fungi that can survive in anaerobic conditions. Now, again, the actual dynamics of which fungi are in those anaerobic cores at which time during the compost succession and progression, I don't know. I don't know if I haven't seen like a paper that's really studied that or looked at that specific question. Could be interesting. And there's some fungi that can also switch between normal respiration and fermentation to get their chemical energy. So, but a lot of fungi tend to prefer an aerobic environment.
Thanks for watching this clip from my new podcast, In Search of Soil. For more great clips and full episodes, check out the links in the description below.